You should write it on a piece of paper, and when your computer, or if your computer breaks, you can always recreate your wallet and get access to your Bitcoin simply by entering these 12 words. Now, there is a second way. If you forgot or you lost your 12 words, you might be able to use your password if you also have the file that includes the encrypted passphrase, and it's always stored on your computer locally. For most wallets, it's in a folder called app data. For some reason in Microsoft, you have to write a percentage, app data, percentage, and then you can get access to the folder which has your encrypted passphrase. Anyway, so I do have my passphrase encrypted. It's in my case, it's in a file called this, but it doesn't matter. I only need to figure out what my password is. So let's go to export keys. They ask for my password. I can enter manually, but there are too many combinations. I will never be able to enter it manually. So I have to have an automated way of trying a lot of passwords until I find the correct one. This technique is called brute force. The good thing about it is that it might, or it will definitely work. The bad news is that it can take you 1,000,000 years. So depending on how good you are at guessing, I mean, how much you're able to limit the subset of characters or set of characters, how much you're able to point it down, the time might be anywhere from a few minutes to a few years to a few hundreds or millions of years. So anyway, let me tell you what I'm talking about. So let's look at the page source. So when I enter a password, I'm taking here, it checks my input, the password that I input, against the encrypted passphrase. It decrypts the passphrase with my input. And if this is a valid passphrase, then it knows that the password okay. And that's all there is to it. But in order to do the brute force, I need to change this code, which I have already done here. Okay, so the code itself is something like 25 lines. It's not very complicated, but I'll just first tell you what it's written here. So the first character can be any character from A to Z, uppercase, or from A to Z, lowercase. It can be a digit, or it can be one of these special characters. And exactly the same for the second, the third, the fourth, the fifth, the sixth, seventh, or eighth character. In my case, I already know that the password is exactly 8 characters. So at least that much I know. And then it creates all different combinations of all these different sets of characters. It loops through. So here you have a nested loop of 8 levels. It's quite massive, I can tell you that. And then it tries the password candidate against the encrypted passphrase. It tries to decrypt it. For some reason it usually leaves an error, but that's fine. That's why you have a try catch. So you have the wrong password, you get an error. In some cases you just happen to get an empty string. And in other cases you get a few characters that don't make any sense. Why the crypto.js library is like that, I don't know, but it doesn't matter. If the length is more than 20, then I know that it has to be the correct passphrase, and the passphrase would be at least 50 characters. So this simple test will tell me that the correct password is found. What more? Brute force, it might take forever, seriously forever. So the first character can be any one of these. How many? Down there you can see 75 characters. Likewise, the second character can be any of those 75 and so on. So you have 75 times 75 times 75, 8 times different combinations, which then happens to be 1 times 10 to the power of 15. and try and guess what does that mean. Well, 1 times 10 to the power of 6 would be 1 million. 10 to the power of 12 would be 1 million, also called a trillion. So here you have even 1,000 times more than that again, so 1,000 trillion combinations. To be correct, that would be 1 quadrillion combinations. Okay, so I did run this script. It turns out that my browser, which I run it in Firefox, is able to try 15,000 combinations per second. So if you look at these numbers, 1 quadrillion divided by 15,000 per second times divided by 3,600 seconds per hour divided by 24 hours per day and 365 days a year. It might take up to 2,000 years to try all combinations. Now, what does this tell me? Well, the obvious answer is, well, I can't wait that long. I have to find another way. One way would simply be to make the algorithm more efficient. I'm sure that whatever I did here, it's not a very efficient way. Maybe you don't need to stringify it. If I start looking into that, it will take me time, and my time is, well, I mean, I could get $200, but it's not worth my time to start looking deeper into this. Of course, I run it in the browser. Browser is not the fastest, it's not designed to do brute forcing, of course. I guess it only uses 1 core. The CPU, it has something like 4 or 8 cores, so just by that you could speed up by 4 or 8 times if you're able to run in parallel on many cores. You could use a GPU. How to program a GPU, I don't know. But that potentially could, I don't know, be 10, 100, 1,000 times faster. But in any case, even if I were able to do the brute force 1,000 times faster, as you see, instead of 2,000 years, maybe it would only take 2 years. Or I could also have a network of several computers to run in parallel. And I mean, if I had 1,000 computers instead of 2,000 years, it could be 2 years. If I had 1,000,000 computers, yes, I would find it quickly. Again, is it really worth for $200 now? What else can we say? Which other approach can I make? Well, so I do remember it was exactly 8 characters, but I also remember I did not use any uppercase letters. So now we're talking. It was not any uppercase letters. So now you see the amount of the set is now only 49. I also happen to remember I used only 1 special character. It was the plus sign. And now we are down to 36 possible characters. So immediately the brute force becomes a lot easier. 36 to the power of 8. Okay, 2 trillion. What would that mean in terms of years to wait? Still 5 years, potentially 5 years. There's something about this though. This is a worst case scenario. So 5.9 years would be the worst case. You might even find it tomorrow. You might find it next year. Statistically speaking, you're expected to find it in half of that time. So you would expect to wait 3 years. Again, it doesn't make sense. However, if you do have a big amount, hundreds of thousands, maybe you would run your computer for 3 years, of course. Or you could just have several computers. Say that you have 2 computers, then you would simply take this file. Your first computer will run an algorithm that looks like this. And the second would run, so the first one would then run through A, B, C, D, through R. And the second would run from S. And by the way, I was a bit too lazy, but of course for every character you would have to do the same. If you happen to know that you only have lowercase, you only have digits, and you only have the letters, symbol plus. Okay, further ahead, I also remember, because I did not use a random password generator, I just used my own brain, which typically is a bad idea, but for my case I just wanted to remember the password, which actually I did remember for a while, but I haven't used it for a few years, and that's why I forgot it. So I do remember that the first character was a lowercase, the second one was also lowercase, the third one was a digit, so I think you see where we're heading. Now the brute force will be much faster. So the third one was, so I had like 2 characters, I had 2 numbers, very easy to remember, or it used to be easy to remember. And then it was something like M or N or something like that. I think it was one of those 2. And here was my character. Plus, and then plus 2 digits again. So, and like typically you would not want to make your passwords like this, or maybe you would, because now I'm actually able to get my password back, but an attacker, a hacker, who would happen to also get access to my passphrase, or sorry, to my encrypted passphrase, he could start to look for combinations, something like this. Having said that, so this I put out on GitHub. It has been public, and anyone in the world could have done this for the last 5 years, but no one did. So I think it was a pretty good password in the end. On the other hand, it was only a few dollars worth of Bitcoin until recently. So maybe no one even bothered, or no one even knew about this. So anyway, so now you see the number of combinations is really small, and it is gonna find my password pretty fast. So let's run the script. So I saved it as export to. I just need to refresh. I will click Ctrl-Shift-I to get developer tools, and in the console you can see what is happening now. Okay, so the speed is something like 10,000 per second. It's because I'm running a screen recorder. Without the screen recorder it would be at 15, but you can see it's working really fast, or quite fast. It's already past 1%. So in terms of brute force, that's very fast, but we have to wait. I tried to do it in Chrome as well. It works in Chrome, but just a lot slower, at about 5,000 per second. So just keep that in mind. Firefox is faster. So of course, when you are running a script like this, you freeze the browser. At least with Firefox, you just click somewhere on the window, and it will give you a pop-up here, not a pop-up, but like this drop-down, and you can click stop if you want to stop the script. Otherwise, it just keeps on going. It can go on for days if you want, or years, doesn't matter, it just keeps going. So of course, if your case is, let's say you have an Electrum wallet, you forgot your password, like I said before, you have to type in app data with all those percentage marks and all that in order to get the file. How exactly you would